All right, so I've already made a drawing. We have a system. Like, this is one where sometimes people look at this and they're like, I just don't even know it. We have a system. Same every time. Draw a picture. Done. Second, establish reference frames. Now, I told you this isn't the same. It's not the same as the last problem. It's not the same as the things that we're doing in class. But really quickly, we can determine that nothing about the forces or motion acting on this object on the ramp are really significantly different. So for all those other problems, we used a tilted frame of reference. It seemed to make sense. I told you that it would make your life easier. So let's use it. And if you chose not to, it's fine. You can solve the problem with any frame of reference. This one will make it easiest, but it doesn't matter. For the object hanging off the pulley, well, we've pretty consistently said, let's just use a standard vertical and horizontal frame of reference. Why? Because there's nothing going on horizontally, and all the forces and any motion is going to be purely vertical, so it makes sense to use this frame of reference. The fact that I chose to make up positive is going to add a little bit of trickiness to our situation, but that's okay. We can deal with it. Okay? So now we've got our drawing, we've got our frames of reference. The next step, make free body diagrams for each object. So ideally, you would have come up with something that looks like this for our 10 kilogram object. There is some force within this string. It's tension, and the way tension works is it's kind of throughout the whole thing. It's this pulling force on either end. So we're just gonna say that we have tension in this direction. We know that the Earth's gravitational field is pulling straight down here, so we can call this M1. And we know it's 10 kilograms, by the way, but I'm still just going to call it M1 because that's just as easy as anything else. Call this object 1 and object 2. And there is going to be a normal force. How do we know there's going to be a normal force? Same way we knew there was going to be one before. In this case, the way these two forces are arrayed, there is no way that this object can possibly not accelerate like in the direction of the ramp at some level. And it's not doing that. So we know it's only going to be accelerating this way or this way. We know that there has to be a normal force. There has to be a normal force because otherwise it would accelerate in some other direction besides this parallel direction of the ramp, all right? So there's our free body diagram, and you may say, well, what about friction? We know there's no friction. If there was friction, this problem would become way more complicated because if there is friction, we don't know what direction it is because we don't know what direction this would accelerate, or indeed if it's going to accelerate at all. It may be perfectly balanced, maybe the same situation that we were looking at here. But because we know there's no friction, we don't have that force in an unknown direction, so that's good. And if we look at our second object, there's two forces acting on it, tension and its mass times the acceleration of an object in free fall. There's a gravitational force pulling this object down. And here it's a little tricky because I know the directions of these forces, but I don't know their relative magnitudes. I don't know which is stronger. And some of you are like, wait a second, they're the same, right? Got two arrows, opposite directions. We've gone through this before. You will make this mistake repeatedly, not because you are like, there's something wrong with you, but because your brain, just like everybody else's brain, is trained to think about this object and these arrows as being in equilibrium. In particular, static equilibrium. And it's not. Okay? All right. So what does that tell us about the relative magnitude of these two forces? They might be the same, might be in equilibrium, or they might be different, and if they're different, we don't know which one is bigger. My drawing is gonna be misleading, maybe, just don't know. So I have to like keep that like filed away in my brain, because I don't know which of these is larger. The tension might be larger than the weight, but the weight might be larger than the tension. I do not know in this situation, okay? And then, so here's our step 2, we've got our free body diagrams. The next piece is to break forces into components. For object 2, that's easy, everything's aligned with our y-axis. For object 1, it's still easy. Not because everything's aligned with our axes, but because you know, anytime you have a tilted frame of reference for an object on a ramp, the components look like this. You have a perpendicular component that's equal to the weight times the cosine of this angle, which is the same as the angle of the ramp, and you have a parallel component equal to the weight of the object times the sine of that angle. Always the same. So here is something to think about with reference to the accelerating cart slab. We're missing a force here that you know is present in your accelerating cart slab. Friction is significant. And you know the direction of friction. Your accelerating cart slab, it says, we want to make everything accelerate up the ramp. So the cart is going to go this way, your weight is going to go this way. For your accelerating cart slab, friction is going to oppose motion. There will be a force of friction down the ramp. For this, it's a friction in the surface. We don't know if it's moving, and if it is moving, we don't know which way it's moving. But we know that there's no friction, so we don't have to put it on there, okay? The next step is to use Newton's second law, and we have several different dimensions and objects to work with, okay? So if we look at this object, object number 1, we have our forces in the x dimension, which should tell us this object's mass times its acceleration in the x dimension. And our forces are the gravitational force in our negative direction. So this is the parallel component of the gravitational force. It's in my negative direction, so I put a negative sign in front of it. The magnitude of this force is positive. And the tension is positive. That's going to equal this object's mass times its horizontal acceleration. Is it accelerating? We don't know. This might be 0. If that's the case, the magnitude of these two forces is the same. It might be accelerating up the ramp in our positive direction, in which case our tension force is bigger. It might be accelerating down the ramp in our negative direction, in which case the parallel component of the gravitational force is bigger. We don't know. So we don't know whether this is positive or negative, and we don't know whether the sum of these forces is positive or negative. If we look at our y dimension, I'm not going to write this out, not because it's incorrect, but just because if you look at the y dimension, what you'll see is there is no acceleration in this perpendicular dimension, which means the normal force and the perpendicular component of the gravitational force have to be equal and opposite. Ultimately, that's not going to give us any useful information. So I'm leaving that out, not because you would know that, but because if I were to add it in, I would just do some work that ends up not getting us anywhere. So just know that it's okay to do that work. In this particular case, we just don't need to. So that's the y dimension, the perpendicular dimension for the first object. And then we only have one dimension to work with for our second object. And the sum of the forces in that dimension will equal its mass times its acceleration. So we have two forces. Our tension is in our positive direction. Our y component of the gravitational force, which is the weight of the object, is in the negative direction. That's going to equal its mass times its acceleration. What do we know about its acceleration? We don't. We don't know anything. This could be a positive number, which would mean the tension is larger and it's accelerating up. This could be a negative number, in which case the weight of the object is bigger and it's accelerating down. They could be equal, in which case they're the same. For the last problem, we knew they were the same because we knew that the whole system was motionless and we knew that the acceleration was 0. The most common mistake people make with these kinds of object on a ramp pulley problems, which are super common in physics, is to assume that these two forces are equal and opposite. That will be true if they're the only forces acting on the object and there's no acceleration. It's not necessarily true in this case. They are the only forces, but it could be accelerated. We don't know which of those is bigger, okay? What are we trying to find? We're trying to find the acceleration of the whole system. So here's something to think about. We know, just like the other problems that we've worked on, where we have objects being pulled along a ramp by a weight hanging off a pulley, we know that the motion of this object, the string, and this object all have to have the same magnitudes. They have to. If the string isn't bunching up or stretching out, then these objects are going to be moving always at the same speed, which means they must always have the same acceleration. Over any period of time, they will have the same displacement. So we know the magnitude of the accelerations of these two objects has to be the same. And that's really key, of course, because we've got too many variables to deal with here if we could potentially have different accelerations. But it also complicates things because while the magnitude of the accelerations are the same, their directions aren't. So this is the other big problem that people have with these kinds of situations, these scenarios. People tend to look at this and think, oh, if this has an acceleration of 2, then so does this. Yes, the magnitude will be 2, but for the first object, my upward direction is positive. If this is accelerating up the ramp at 2 meters per second squared, object 2 will be accelerating straight down at 2 meters per second squared. That's its negative direction. We have a third relationship we can use here, which is that the overall acceleration of our system, if we say that that's the same as the acceleration of this 10 kilogram object, that will also be equal to the opposite of the acceleration of this 5 kilogram object. This this 10 kilogram object's acceleration will always have the same magnitude but the opposite sign, the way that I've set up my frames of reference. So what does that mean? That means I can do some fancy substitution with my accelerations. If I just look at this first this first object, then I can substitute A everywhere I see AX. So that means negative m1g sine theta plus the tension is equal to m1 times the overall acceleration of our system. If I look at this acceleration, the y acceleration of the 5 kilogram object, it's going to be equal to the negative of the overall acceleration of our system. So that means that the tension in our string plus the weight of that 5 kilogram object in its negative direction is going to be equal to negative m2 times the overall acceleration of our system. What are we trying to find? We're trying to find acceleration. We have two equations here. We have two unknowns. One unknown is tension, one unknown is the acceleration, the overall acceleration of our system. So there's a couple different ways that we could solve this. What I would do here is I would actually add these equations, I would subtract one of these equations from the other to get rid of tension. Some of you probably remember how to do that, but let's assume that you don't. And instead, what we're going to do is we're going to solve each of these equations for acceleration. This equation, if I solve it for acceleration, tells me that acceleration is going to be negative m1g sine theta plus t, all divided by m1. This equation, if I solve it for acceleration, is going to tell me that acceleration is t plus negative m2 times g, all divided by negative m2. This acceleration is the acceleration of our system. This acceleration is the acceleration of our system. They have the same acceleration. I can set this term and this term to be equal to each other. Negative m1g sine theta plus t divided by m1 equals t plus negative m2g divided by negative m2. Now I've only got one unknown, and I'm not going to solve this anymore because the rest of this is algebra. Here's how you would do it. First, solve for t. So you like multiply both sides by m1, multiply both sides by negative m2. You'd have t on both sides, you'd do some combination, you'd do some solving, you'd end up with t equals something, and you'll have a number. Because you know m1, g, theta, and m2. And then you can plug t back into either of these equations. Now, like I said, I would do it differently. I'm showing you this because I think most of you would be inclined to go down this road, because you probably don't remember the whole like systems of equations thing. Most of you, this is going to be your approach. There's easier algebraic ways to do it, but this is how I suspect most of you are going to end up doing it. You'll solve for acceleration because you know that's what you're trying to find. You end up setting these things equal to each other, solve for t, substitute back in, solve for acceleration. The easier way to do it would be to just subtract this equation from this one. That will get rid of t. And then you solve the resulting equation for a, and you're done in fewer steps. But it's all, you'll get the same answer either way, okay? So how does this help? This helps with our accelerating carts lab in a couple of ways. One is the free body diagrams, while they're not 100% accurate, are pretty close. Two, this relationship right here, depending on how you set your frames of reference up, is probably accurate. If you set your reference frames up the way that I did here, then the acceleration of your system, the magnitude of the acceleration of your system, will be equal to the positive acceleration of your cart and the negative acceleration of your hanging mass. So that's going to be useful too. And then the only other piece here that you're going to need to take into consideration is that there's a force of friction. That's not in this problem, but it is in the accelerating carts lab. Okay? All right. That's my piece. Does anybody have any questions? Okay, so what we did earlier was designed to have you think about what you're able to do. So don't think about it in terms of like your grade. Think about it in terms of what are things that you need to practice. Like how close did you come on the free body diagrams? How did you, was this the only thing that you messed up? And do you understand this? If this was the only thing that you got wrong, but you really deeply understand why it is that we have this weird sign reversal here, that's pretty good. You're in great shape if that's the only thing. On the other hand, if you fell into the, oh well, these have to be equal and opposite trap, that's a big deal. Because in our case, with acceleration of our system, that is going to lead you to an incorrect assumption, which is that the tension and the weight are always the same. That's not true at all. I mean, I can take an object and I can have the tension be the same as the weight. I can have the tension be greater than the weight. I can have the tension be less than the weight. I can have the tension be way less. Look what happens when I have this tension go to 0. Look what happens to the string. Did you see that? It went totally slack. The tension was 0. This was in free fall. It was accelerating down with no tension at all. It was accelerating down at a rate of 9.8 meters per second squared. Okay, so let's see what you can do. I'm gonna ask you to make some free body diagrams because that's what I want to see, and it may be for what we're doing here, or maybe for other things. All right, you guys have the rest of the period to write.
You mean making free body diagrams in general?